atomic mass, the values that are in the chart for the atomic mass of every element, has been figured out experimentally through a technique called mass spectroscopy or mass spectrometry. We're going to talk briefly about the process, but mostly about the output and how the information we get from the process of mass spectrometry helps us to calculate the average atomic mass, the values that you find in the periodic chart. So the first thing we need to remember here is this idea of isotopes. For any sample of an element, while the atoms are identical in terms of the number of protons they have, and assuming that they're not charged or ionized, they all will also have the same number of electrons that correspond to the number of protons. But they can have more or less neutrons. So that means they can be heavier or lighter. They can have more mass or less mass. And so since they're all the same element, but they're different versions of that element based on mass, we call them isotopes. So for example, here we have the 3 different isotopes of hydrogen: protium, deuterium, and tritium. Almost all of the naturally occurring hydrogen is protium. It's just one proton with one electron circling around. But there is a small amount that has picked up a neutron, and a very, very small amount, mostly resulting from human manufacture because of radioactive, using water in nuclear reactors that absorb extra neutrons. You also have tritiated water, so hydrogen or heavy water that has picked up 1 or 2 neutrons. Okay, but most of the hydrogen is the isotope that only has a mass of 1, which is why on the chart, the average atomic mass for hydrogen is 1.001. The 001 comes from the small amount that has a neutron that has a mass of 2, and the very small amount of tritium that has a mass of 3. So the process of mass spectrometry. You take a sample of an element and vaporize it, turn it into a vapor, and using a vacuum pump, put it at extremely low pressure, like almost no pressure, practically a vacuum. So there's very few particles. And then there are different methods by which we can rip away some of the electrons, disrupt the structure, so that they become charged ions. The atoms become charged ions. Using an electric field and a magnetic field, we accelerate them through, and it works on the premise of separating the atoms based on their mass to charge ratio. So the heavier ones are more massive for the same amount of charge or ionization, and ones that have less neutrons would be lighter. And so their path is affected by the magnetic field they pass through, that they're shot through, so that they bend at different rates, and then there's a detector that picks up where the atoms, if you'll, land, and a computer takes all that information and calculates out what's the mass to charge ratio, so therefore what's the relative mass distribution of all of these results. Long story short, we put it through this machine, we get results. The results come out as a graph of relative abundance based on the mass to charge ratio. And so from that, we calculate what the average atomic mass is based on the ratio and how many of each type of ratio. So for example, here we have boron, and here's 2 results from a mass spec of a sample of boron. So the relative abundance of boron 10 is 23, and of boron 11 is 100. So how do we figure out the average atomic mass? We multiply the percentage by the result we have, sum them up, and divide it by the total output. So even though that relative abundance isn't truly a percentage, sometimes they're as percentages, sometimes they're as actual relative numbers to each other. So in effect, we weight each one based on how many we get at that particular mass out of the total distribution. And so that's where, for example, boron, the average mass comes out to 10.8. Okay, so what's really relevant for us to understand here isn't so much the mass spec process. That's not the goal of this presentation, as much as understanding what the results are that we get out of it, and then how we use those results to calculate an average atomic mass. So from this result from mass spectroscopy, we then can have a mole fraction or a percentage for each value that's relative based on charge to mass ratio, or mass to charge ratio, I should say. So for example, here are the 4 isotopes of lead. And as a result of analysis, we have some very detailed values for the relative atomic mass of each one. When we say relative, they're all compared to the carbon-12 standard, referring to the most common form of carbon, the most abundant form of carbon, as having an atomic mass of 12. So from these results, you can see that 1.4% of the lead in any sample weighs about 200 and just under 204 atomic mass units, and 24% is just under 206. 22.1% is just under 207, and over half, just over half of all the lead atoms in a sample typically weigh 207.97, so just under 208. So if we take all those informations, and sometimes they can be expressed as mole fractions or as relative abundance like in the last slide, but they could also be expressed as percentages, in which case you just turn them back into the decimal, and we multiply each relative mass value by its fractional amount in the sample. And so here's a picture of my working through. So taking the value for the lead 204, multiplying it by its mole fraction or its percentage in terms of relative abundance, I get a value. Do the same thing with each of the other 3 isotopes of lead and have a sort of weighted value for the amount that they're contributing to the overall mass of all the lead that's in the sample that was assessed. And when I add them all up, I now have the value that you find on the periodic chart. So that's where they come from. So we use mass spectrometry. We get relative abundance values for how many based on their mass to charge ratio out of the machine. And from that data, we assign values that then allow us to calculate what the overall mass is based on how much of it is a lighter isotope versus a heavier isotope. So it's not just simply adding up the mass of each isotope and dividing by the number of isotopes you have. It's also what percentage do we find of each isotope in naturally occurring samples.